Okay, so this is the subspace span of V1, Vn. We choose Vn plus 1 until Vn from the subspace orthogonal to the orthogonal complement of this subspace, of this span space. The Vn plus 1, Vn plus 2 until Vn are chosen from the orthogonal complement of our this subspace. Then we can choose the Vn plus 1 Vn to be the orthogonal basis for the space, orthogonal complement of our given subspace. Okay, that is to say Vn plus 1 Vn are orthonormal. Orthonormal means that their length, their norm is 1, and they are orthogonal to each other. So this form an orthonormal basis. This m minus n vector are orthonormal basis of the orthogonal complement of V1, Vn. So this is the extension of our linearly independent vector to get a base for the whole space Rm. Now we want to prove that the given vector V belongs to the span space of V1, Vn. The condition is that whenever a vector orthogonal to the span space, then this vector will orthogonal to V. That is, H is here. So geometrically, H is orthogonal to the span space means H belongs to the orthogonal complement of our space. Then our V will perpendicular to this H. So obviously V belongs to the span space as indicated in the conclusion of the lemma. But this is a geometric intuition. We need an analytic legally prove this result. How to do this? Obviously we can write V to be a linear combination of the basic vector Vi. Then we want to prove that kappa n plus 1 until the last one are all 0. Once we can prove that the last n minus m coefficient of this linear combination are 0, then V is simply a linear combination of the first n vector V1, Vn. Therefore, V belongs to the span space as we want. Okay, so this is the idea to prove that V belongs to the span space. So that is right. V to be the linear combination Ki Vi. Because V1, V2, Vm are the basis of Rm, therefore we can find the Ki so that this is true. Then we need to prove that Ki is 0 for I greater than or equal to n plus 1. Once this is proved, then V is the some linear combination of V1, V2, Vn. So belongs to the span space of V1, Vn as we wanted. Okay. So how to prove that all these Ki are 0? It is very easy. Since Vj is orthogonal to the span space of V1, Vn, whenever J is not less than n plus 1. Okay? Because as I said before, Vn plus 1, Vn plus 2 until Vn are the orthonormal basis of the orthogonal complement of this span space. Therefore, Vj has this property perpendicular to this span space. So our 0 would be the inner product of V and Vj, right? This is our assumption. Our assumption is that whenever a vector is orthogonal to the span space of V1, Vn, then the vector will perpendicular to V. Now our Vj here is perpendicular to the span space, so it is also perpendicular to our V. So the inner product is 0. But this inner product we can compute explicitly. That is I from 1 to n ki vi then vj. Of course, this is I from 1 to n ki vi and vj, inner product of vi and vj. But sorry, this is m. V is the sum of I from 1 to m, not n. So this result is kj. Why this is kj? Because for I1 n, the vi vj is 0. Okay, and for I greater than or equal to n plus 1, vi vj is delta ij. That is if I equal to j, then the result is 1. Otherwise, the result is 0. So using this property, you will get the final equality. So this proves that when j is greater than n, then kj is 0. The coefficient kj is 0. Therefore, our v is really the linear combination of v1, v2, vn. So belongs to the span space. Okay. So this proves this lemma. So with this lemma in hand, we can give a new proof of the third proof of the Lagrange multiplier theorem. Okay, so we draw a picture, geometric consideration. This is also a geometric proof. So this is our m. That is the 0. And x0 is the minimizer in m we want. This is x0. So x0 belongs to m is minimizer of our function restrict to m. Therefore, we take any curve for any we take an h for any h belongs to the kernel of the derivative of g and x0. That is the subspace h in Rm. G prime x0 h is 0. Okay, for any h in this linear subspace. By our previous theorem, because g prime x0 h is 0, so by the previous theorem, the inverse problem of the normal vector, we proved the theorem at the very beginning of today's lecture. Remember, we know that the gradient of a function is perpendicular to the tangent vector of every curve on the surface passing the point. Okay, but conversely, if you know h is perpendicular to the gradient, is there a curve in the surface passing the point and which that vector as a tangent vector? This problem we considered at the beginning of today's lecture, and the result is positive. We have an affirmative answer. So since h, the theorem we proved there is that if h is making this 0, then there exists a curve on the surface passing x0, and which this h as tangent vector at x0. Okay, So we have a curve. The curve is lying on the M, passing the point x0, such that the tangent vector of the curve at x0 is our H. Okay? This is the result we prove at the beginning of today's lecture. But x0 is the minimizer of f considered as a function of defined on M. Therefore, t equal to 0 is a minimizer of t equal to 0 is a minimizer of the composed function f gamma. Okay, so here is epsilon 0 minus epsilon. So this is the curve gamma, and our function is defined on M. Our function is defined on M f. Then the composition of f and gamma is a function defined in the interval minus epsilon to epsilon, defined in this interval. So because for every point near x0 on M, the value of f at that point is greater or equal to x0, but x0 corresponding to t equal to 0. So for t near 0, gamma t is very close to the point x0. So in conclusion, the t equal to 0 is the local minimizer of the composition function. So this composition function is differentiable. So we know that the derivative of this function at t equal to 0, that is this by the chain law. By the chain law, this is the gradient of f at x0 in the product with gamma point 0. That is the gradient at x0 and h. Okay. So this means that whenever h belongs to the kernel of the derivative metric of g x0, whenever h belongs to the kernel of g prime x0, but this kernel, you know that g prime x0, g prime x0 is the g1 gradient of g1, gradient of gn. Okay, so h belongs to the kernel of this metric, means that h is perpendicular to the span space of g1 x0, gn x0, right? So if these are equivalent, h belongs to the kernel is equivalent to the fact h perpendicular to the span space of the row vector of the metric. That is the gradient of g1, gn at x0. So our previous argument says that whenever h is perpendicular to the span space of the gradient of g1, gn, we have h is perpendicular to the gradient of f at x0. So using our previous lemma, we conclude that the gradient of f at x0 belongs to the span space of the gradient of g1, gn at x0. So this is precisely the conclusion of the Lagrange multiplier theorem. Okay.